that we did not get finished with this. I think this is like the third day of two-dimensional motion, but the first one we really just kind of was a real quick introduction. I think yesterday was the first day that we like really got into it. So the and yeah, and the good news about this one is that this one is not analytical. So as long as you can plug in the numbers, and you have to pay attention to the situation at the same time, because I think we came out to right before we left the fact that if you plug in VI and VF at the beginning of the trajectory and the end of the trajectory, it's going to be exactly the same. So the total displacement is zero. If you're looking for the height, you can't do that. If you're looking for the height of the object, we're going to have to use half of that velocity. So we're going to be using the initial velocity being 34.4 and the final velocity being 0 meters per second. We're using 34.4 because even though it says 60 meters per second, we're only counting the vertical direction of motion, which would be 60 times the sine of 35, which is why we're using 34.4. And it doesn't look like I actually got a number for that distance. I think that's where we left off on Friday. So that's what we need to get. It's 60 meters, is it really? Okay, I'm about to say, I was like, that doesn't sound right to me. I may be, I may not be good at arithmetic, but that doesn't sound right to me. So, let's see. I can erase this part, I think. There it goes. It's just a little slow. It's Monday for the computer. It's like, I don't want to. I'm going to move this over to the other side, so it's negative 34.4 squared, and then negative 2 times 9.8 d. I went ahead and I made this. This is negative 9.8. So what do we get? I need a calculation and I need a second. Well, I'm solving for the distance or the displacement here. I'm solving for the displacement here. This is 2 times 9.8, not 2.9.8. It is not an IP address. It is, there we go, 2 times 9.8. Yeah, so yeah, the squared will automatically make it positive. So we subtracted it over to the other side, and then but you know what? You could square it beforehand and then subtract it, and that would also keep it negative. So scary, because that way the negatives will at least cancel each other out. Yeah, because the negative 9.8 meters per second squared for the acceleration. What's it come out to be? I think so, but I'm gonna need y'all to do it. I'm not doing it for you. I need a answer and I need a second. Apparently, apparently several of y'all are not feeling the calculations today, but that's okay. I will wait. I am a patient person. Is this the square or is this the? Are y'all giving it to me in steps, or are you just gonna give me the final answer? It doesn't matter to me either way. Either way is fine by me. Okay. 60.4? Really? Oh, big brain time. I don't know. Yeah, I think somebody I think you just won the lottery. 60.4. Now, is there a second to that or did anybody else get 60.4? Y'all double check it, right? Divided by. Okay. Okay. Yeah, you definitely don't want to subtract. You're going to divide both sides by 19.6, which is 2 times 9.8. Should we get 60.4? Is everybody okay? Yeah? It worked? Okay. Well, then the displacement is 60.4 meters. That's going to be the height. So the height of the trajectory is 60.4 meters high. Okay, using our VF squared equals VI squared plus 2AD. Now, what about the time? How long does it take to actually make that trajectory do its thing? How long does it take that trajectory to do its thing? Which equation would we want to use? Okay, which one is the easy one? Number 2? Okay. We have everything, I think. Just make sure that whenever we use these, that we're using the vertical ones. Make sure you're using the vertical ones. So what is the VF? Uh, 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 well, okay. Which one are we going to do? Are we going to do 0 or are we going to do 34.4? Why 0? Okay, so if you do the VF is 0, then you are calculating this part of the trajectory, right? Okay, so we can do that. We can do that. Yeah. So if we use 0, we're going to have to double the time. Okay? If we use the VF being negative 34.4, we don't have to double the time. The answer is just the answer. Which one do y'all want to do? Negative 34.4? Right. The last time we did it, that kind of bit us because we got 0 equals 0. But this time, since we're looking for the whole time, that'll actually work out. So negative 34.4 for the final velocity equals 34.4 for the initial velocity, plus negative 9.8 times time. No, but they're gonna try every single time now because they got lucky. Now they're gonna try every single time, and we must suffer because of it. So we're gonna subtract both sides by. Okay, and what do we get from that? No, uh, negative 68.8. Okay, negative 68.8. Negative 9.8 times time. So we're gonna divide both sides. Time is it 7 on the dot? 7.02. That's close enough for me. Yeah, so our time is going to equal 7 seconds. So if this thing gets launched in the air at 60 meters per second, which is like 120 miles per hour, it's going to last in the air for 7 seconds. Most things, like, yeah, even if you throw like something really fast, like a baseball or something like that, it won't last in the air for longer than like 6 or 7 seconds. Anything past that, and you're dealing with like inhuman territory. So I'm gonna put like 7.0 seconds, and like even if you're talking about like golf, for example, they sling that stuff way high in the air, but it still ends up like coming back. Usually in less than 7 seconds. Okay, unless you're really hitting that fast. I think we're done now. What else do we need? We need the x. Oh, we do need the range. You're right. We still need to find the range um we still need to find the range of the trajectory of the projectile. So that the whole trip was 7 seconds. Yeah. So what do we do? We do not need to use the fourth equation. So for the range, do not use the fourth equation. For the range, do not use the third equation. For the range, do not use the second equation. For the range, do not use the first equation. Why? 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 There we go. There is no acceleration happening over here. So velocity is just distance over time. So is or displacement divided by time. Okay, so we have two of those. We have the time and we have the velocity. Okay, so If we solve this for displacement or the range, displacement is velocity times time. So we're going to do 49.1 times 7. No? Why? What? So, what's it come out to be? 343.7 meters. Okay? Because that's velocity times time. I told you he's going to guess every single time now. And that's just gonna have to once you get lucky with that kind of stuff, you just like immediately start trying it every other time, and we're just gonna have to suffer because of that. Okay. All right. So here we go. Yeah, y'all's test on the kinematic stuff is gonna be Thursday. Wednesday is gonna be if y'all have any questions. So that digital day, I'm gonna have a Google Meetup, and if you guys have questions, you can just come in and ask me, and I'll be there. So like you don't have to be in there at all. So like if you don't have any questions, then just say, "Hey, I'm reviewing for my test," and then we're good to go. Um, no, you should definitely review for your test, right? So that's going to be what you guys are going to be responsible for. So if you have questions on the digital day, come into that Google Meet and let me know because I'll post a link and I'll have it on from 8 a.m. to 3 p.m. and y'all just hop on whenever you want to, and I'll get it done. I should have the videos done before school even starts. Uh, yeah, and on the exam, I don't think I'm going to have any hard two-dimensional motion problems. I don't think they're going to be like super difficult. So well, I think they'd actually be a little bit easier than that, to be honest. So the whole point is that there is no acceleration in the x direction. That's really what we've got to focus down on. Okay, let's take a little bit of time and talk about complements. Yeah, so like angles. So like if you deal with complementary angles, what does that mean? Supplementary is 180, complementary is 90. And in physics, when you're dealing with trajectories, a complement is actually a really big deal. So like if this is 20 degrees, the complement of 20 degrees would be this angle, which is 70 degrees, right? Because they'd both add up to 90. Complements of trajectories have the same range, okay? So complements have same range. Okay. What changes though is the speed, the horizontal speed. No, sorry, the vertical speed and the time. Okay. Because if you think about it, a 70-degree incline or a 70-degree launch will stay in the air longer than a 20-degree launch. So let's say I'm going to launch one at 20 degrees like this, and I launch another one in the air at 70 degrees. This one's a lot more pitched, but it ends up hitting the ground at the exact same spot. Okay? There's only there's only one angle that doesn't have a complement. 45 degrees, its complement is itself, right? So because of that, here's a little cheat mode. So if you've got a 45-degree angle, a 45-degree angle has the largest range. Okay, so 45 degrees is largest range. If you go past 45 degrees, then you will stay in the air longer, but your range won't be as far. Okay, so this is one of the reasons why we don't launch rockets at 45 degrees. You want them to last, and you want them to be in the air a little bit longer. Also, whenever they are falling back to the surface, they gain speed from falling back down because of gravity. So you want them to, you don't want to launch it at 45 degrees. Okay. Uh, no, we don't want to do that. Okay. So every single launch angle has a complement that will hit the exact same angle or hit at the exact same range as it. Okay. The difference is this one this one at the bottom has a low time and a high horizontal speed, a high Vx. okay, because it's going to move this way and it's going to move there quick, okay? The one up here has a high time, but it also has a low Vx, okay? Has a high time, that almost looks like height, I'm sorry. That looks like it's a high time, high T, there we go. And it has a low uh, horizontal velocity that goes along with it. And I think that's really kind of all I need to say about that one. It's not too bad, and there's no math involved with that at all, except for like adding angles to 90 degrees. So if you see two of them that have get launched at the same or complements of each other, their range will be identical. Okay. Now there is a range formula. There's a formula for the range of a um, there's a formula for the range of a projectile, but it is not given on the formula sheet. Okay, so if you need to solve for the range, you would have to memorize it or do the DVAT that we just did. Okay, the DVAT will do it, but there is an analytical answer. But I warn you, the analytical answer has some trig in it. Okay, you're okay with that? Just give us the answer. Okay. Now, I don't think that you would ever, even in AP Physics, I don't think you guys would actually have to derive the formula because there is trig identities involved in it, and trig identities is not something that I see very often on the AP Physics exam. I've never seen it happen at all, aside from maybe some sine squared plus cosine squared equals 1. But other than that, I haven't seen anything like any double angle or half angle stuff at all. So the formula for the range of a projectile is in Google. No, but you can right now. V squared sine. So range is equal to, y'all tell me what it is. What do we get? Hopefully, and I'll know if it's right. Yeah. Negative. Did you find it? Uh-oh. I don't know. That is it's the first one. Yeah. There should be a yeah, there should be a fraction involved in there. You might want to find one that actually has more of a fraction. That one just kind of looks like alphabet soup and somebody typed it in there. No, maybe we just don't need to have that one. Maybe we should. I mean, yeah. There we go. Okay. So, did you just tell me that it is v squared times the sine? I know, but I don't use u. Of 2 times the launch angle over g, like that. V squared sine 2 theta over g. Okay, did you get a second? Look at the same. Okay, this is the formula. That sine of 2 theta, if you were to actually go in and derive it analytically, you would have to use a double angle identity to get there. And instead of taking the whole period to do that, this is the formula for it. You can use this formula on the AP Physics test if you need to, but it is not on the formula sheet. Okay, so you cannot rely on having it there to memorize. So this is not on the formula sheet. Okay. Okay, so like this is this is a forbidden equation. Okay, although I will tell you this, the range formula won't be as useful to you as the original forbidden equation. So if you had to pick between memorizing the range formula or the fourth forbidden equation, I would pick the fourth forbidden equation. Okay. Yeah, so like if that forbidden one is in there, then use that one. The range one is situational. It may not show up on the AP Physics test at all. So I just thought I would go ahead and throw it out there in case you guys needed it, because it would be a really quick way to solve for the range without having to go through the DVAT of doing two problems, your X direction and your Y direction, and then solving them out. You could literally save yourself a lot of time. If there is an AP Physics part that actually asks and talks about the components, obviously you would need to break them apart. Don't just write down the formula and be like, I am so smart, because they won't give you any points for it. Okay, so, but if you need it, it's totally there. And we could talk about the dimensions of it to see if it's dimensionally correct, but I think we probably need to move on with our life. Do we want to try another two-dimensional motion problem, or do we want to talk a little bit about the last thing I need to talk about? Last thing? Okay. The last thing that we're going to talk about is this little concept called relativity. And we're not necessarily talking about like Einstein's relativity. So let's see, did I spell that right? Relativity. Yes, I did. Okay. So, and relativity does exist in a classical sense, and that's what we're talking about here. We're not talking about the stuff that Einstein came up with. We're talking about relativity to us. So, and what we're really going to be trying to focus on here with relativity is we're going to be focusing on things called a frame of reference. Okay, a frame of reference. And what that means is basically a frame of reference is a viewpoint. So if you're like out in the middle of a field and you're watching a car go by, there are two different ways to think about this. This is my car, fancy car. So, and this is also it's a convertible. Uh, there are two different ways to think about this. If the frame of reference is centered around you, then, and I'm going to draw like a little plus sign, like a little crash dummy symbol for this. If the frame of reference is you, then you observe a car driving by at 60 meters per second. Okay? And if the frame of reference is the car, then the car observes you going by at 60 meters per second. So here's our. So if this is the frame of reference, which I'm going to draw as this, if this is the frame of reference, then the car sees you going this way at 60 meters per second. Okay, now here comes the fun part. Who's right? They're both right. Yeah, and y'all pretty much nailed it on that one. Like y'all are just like, I don't know, for some people it has to be like one way or the other way, and whenever I say they're both right, their brains start melting a little bit because they're like, wait a minute, how can both of these situations be right? It all depends upon your frame of reference. So if you're the one standing still, and you got to think about like how the camera is moving. So if the camera is with the person on the right side, and that camera is standing still, and the car is moving past the camera, okay? If the camera is standing still here, or sorry, if the camera is in the car, then the camera is going to look like it's standing still, and the stuff is going to be passing by it. So it's all about the frame of reference of the motion itself. So both of these situations are correct. And if we do the kinematic equations, if things start to accelerate or decelerate, then the kinematic equations actually work out in both cases. So that's kind of strange as well. So let me give you guys an example of using relativity with like equations. Say you got two people inside of a car, or sorry, not two people inside a car, two cars. So I'm going to make car A look like this, and I'm going to make car B a little bit further ahead, and car B looks like this. Well, I don't know. I was a little off on my horizontal lines. Car B looks like this. Okay, so If there's no acceleration involved, this is just simple addition and subtraction. So if car B is going at 60 meters per second and car A is going at 80 meters per second, how fast does it look like car A is going compared to B? So A compared to B looks like it's going at 20 meters per second, right? Okay. And how long would it take them to catch up? There you go. How far away are they? Let's give it a distance. Okay. So you're asking the right questions. The right question is how far away are these things? So what if they're 100 meters apart from each other? Okay. Because it's 20 meters every second, right? So it'd take it about 5 seconds to catch up. Okay. How fast is B moving compared to A? Negative 20 meters per second? How long would it take for B to catch up to A? Still 5 seconds. It's the same amount of time either direction. So, regardless of how you think about this, if you think about it as car A moving forward or car B moving backwards, it is the same amount of time for both situations to occur. So, the motion is relative and it depends on your frame of reference. Okay. Uh oh. Uh huh. Uh huh. Uh huh. So the 80 meters per second is one from Texas. How fast? That would be about 160 miles per hour. So you've got car A moving at 160 miles per hour and car B moving at 120 miles per hour. So both of these people are crazy. And this is from some Mad Max scene or something. I promise you. It's just like they're just going. They're going. It's happening. Okay, so like if there's no acceleration involved, the relativity is very easy. Okay, now, what if instead of it taking 5 seconds, what if the time involved was 4.5 seconds? So the time was 4.5 seconds instead of 5. So that means that there was a displacement that occurred, and the displacement was 100 meters. The VI was 80 meters per second. The VF was, don't know what the final velocity is, right? And the acceleration, we don't know the acceleration either, right? Can we find out how fast that they would have to go in their acceleration? Okay, it's a DVAT problem, right? Okay, so it is a DVAT problem. And which equation would we use? Well, either A or VF or both. I mean, I don't do both at the same time, but I either need to find acceleration first or I need to find VF. I, okay. We well, is that what y'all want to do? Okay. The proposal was we can use the forbidden equation to find VF, and then from finding VF, we can find A. So, what? By the way, what is the forbidden equation? VI plus VF over 2T like this, all in parentheses. Please and thank you. Yeah, so VI plus VF over 2 times time. We have D, it's 100. We have VI, that's 80, plus, I don't know, divided by 2 times 4.5. Okay, so what do we do first? How are we going to simplify? Well, so I would argue that if you do 80 divided by 2, that's 40. You would get 40 plus VF over 2 times 4.5. I would actually argue that that's not simplifying. I would argue that the simplest way to solve this part is to multiply both sides by 2, and you would get 200 is equal to 80 plus VF times 4.5. And then you can divide both sides by 4.5. and then subtract 80, and then you got your VF. What's it come out to be? One, no, 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 no. You are doing it opposite. You've got to divide first because both of these numbers inside, the 80 and the VF, are both multiplied by 4.5. So I need to divide by 4.5 first and then subtract 80. Negative 35.5? Okay, negative 35.5 meters per second. Uh, you sure it's negative? How? Yeah. Okay. Okay. So, how do we get a negative number from that? So if we're going from B to A, that'd be a negative 100. Well, okay. So here's the thing. If you're going, something can't be right here. Something in our DVAT has to be wrong, because if we're starting at A and we're going at 80 meters per second, right? And we're trying to cut, they're 100 meters apart from each other, okay? And we're trying to find out how long it takes to catch up. And y'all told me that if one of them is going 80 meters per second and the other one is going 20 meters per second, that is like having a velocity of. Okay, so I think what we need to do, and this is our problem, is that our velocity relative to each other, if this one's going 60 and this one's going 80, then your velocities relative to each other, because these are both going 60 meters per second, right? So we don't need to use 80 meters per second for our velocity. So if we want to try to solve our problem using relative motion, then we're going to have to say that our VI is 20 meters per second. So I'm going to change that number inside here. I'm going to change that 20 to 80. See, our numbers were not realistic whenever we solved that equation, right? Anyways, it's 24.4. So we did accelerate a little bit, right? So we started off at 20, and then our final velocity relative to the other car is now going to 24.4 meters per second, which means if we want to bring it back into context of this, because where is the camera here? Is the camera with A or B? We're with neither. Okay, because think about it. If we're seeing A move and we're seeing B move at the same time, we're just a camera looking down at these two cars that are moving, and the camera is standing still. So what we're doing whenever we put in this 100 meters and this 4.5 seconds and this 20 meters per second, we are making the problem like our camera is at B. Okay, yeah. What's up? Oh, nice. Um, now, what's the acceleration? What's the acceleration? Okay, so VF equals VI plus AT. VF is 24.4, VI is 20 plus A times 4.5. Okay, what's that come out to be? 0.9778. That's way too many decimals. How about 0.98? Right? 0.98 meters per second squared is for the acceleration. Okay, my question for you is, if we flipped the problem over and if we solved it the other way, would we get the same acceleration? What do you mean by complete opposite? Like, define for me complete opposite. Okay, so so opposite in a negative sense means opposite in a math sense means negative, right? So like if we made our camera at A and we looked at the velocity of v, v would be actually slowing, it would be decelerating, right? Which I should not use that word, is v was accelerating in the negative direction, and it would have a negative acceleration direction of negative 0.98 meters per second squared, and it would give us the exact same numbers and the exact same time and the exact same speed, and we could work it that way as well. Do we want to try that, or y'all believe me? You believe me? You do not believe me. You believe me? Okay. I mean, like, it's up to y'all. I can work it this way, but I'll tell you, it'll work out the same. We're good? Good vibes? Okay. So in that case, here's the point. The point is pick a reference and then just stick with it. Don't change references in the middle of the problem. When we made this reference of our DVAT, we assumed that we were looking at B as the camera center and A was actually moving towards the camera. So we made the mistake of putting in the initial velocity of 80 meters per second, but that was because we were using two different camera positions in the same problem, and that's not good. Okay? Always use the same camera position in the problem. Okay? Does that make sense? I have two groups. There's a red cone group and a red bowl group because all of my group colors. I have 6 groups, right? Well, one of my classes has 7, so I had to add an extra one, so I just made a red bowl instead of having to come up with a different color, because red, orange, yellow, green, blue, purple is normally the way to go. Okay, how much time do I have left? Okay, so I think now is a good time to unlock the next homework assignment. So I think that's all that we have to do for notes. So I'm going to unlock the next homework assignment, and we're going to work on that for a little bit. And I'm going to let you guys have at it. Digital people, it's going to be there.